Hi, my name is Dan Aukus, and today I'm going to show you how to make a robot in SOLIDWORKS and then create the manufacturing design for it in PopUp-CAD. The first step is to make a new file, a new part in SOLIDWORKS. This is where you're going to hold all of the dimensions and the drawings which will define the multi-layer robotic device. Now, since we're doing laminate robot design, you want to define everything in a sketch, and then all of this geometry will be determined in a single place. So what we're doing right now is we're outlining or creating the outline of the robot, which can then be dimensioned, and the same sketch can hold the inner scores and folds of the robot design and cuts, but they need to be made out of construction lines. There are a variety of mates which can be used in SOLIDWORKS to define what type of device you want. Some of the common ones are to make lines collinear, to make a point on a line coincident, to make things horizontal and vertical, to give things dimensions. And all of these are possible by selecting the piece of geometry that you care about and then selecting the relation that affects that creates the desired effect. Now what I'm doing is I'm drawing in the inner folds and cuts and scores. Some of these lines will be used to separate different parts of the robot, and other of these lines will be used to determine the bending of each face. You start to see the robot that I'm designing here. Sometimes SOLIDWORKS adds more constraints than you actually want. In this case, I'm trying to make a horizontal line that is not located directly at the midpoint of the line I'm connecting it to, but SOLIDWORKS adds that constraint, so I have to kind of redraw it. Here I'm adding the final cuts or the final folds. I use the trim tool to separate. So now that the sketch is designed, I can make a planar surface out of it. And a planar surface is simply a two-dimensional entity that has some planar properties in this case. Once I've created the planar surface, then I define sets of lines which I'm going to use to separate that surface into multiple faces on the same surface. So I extract in a new sketch several of these lines, and then use the curve split line option to separate that surface by selecting it. And then what you see is you have several faces on the same surface. You have to repeat this process several times because you can't select every single line in the same sketch, and this is because you have to have continuous chains of single lines rather than radiating lines from a single vertex. So you have to do several sketches to fully split the surface. The Convert Entities tool is what I'm using to change the reference line into a sketch line. So all of those split lines are derived from the original sketch. Meaning if I were to change a dimension or or move a point around in that original sketch, then it would propagate. This step is I'm using the offset surface function to create new surfaces from the faces of the one original surface. And the purpose of this is to actually create independent surface bodies in SOLIDWORKS. Because once you do that, then you can create independent solid bodies from each of the surfaces. So this workflow allows you to slowly separate the one sketch into multiple bodies, which can then be exported into an assembly. The next step is to use the thicken feature to thicken each surface into a solid body. When you're using the thicken tool, you want to deselect the merge result option when you are making subsequent thicken operations, because the result will be that it merges the newly thickened solid body with anything surrounding it, including the previously thickened solid bodies. And the whole point of this exercise is to create separated bodies which can be imported into an assembly. So if you do that, you're kind of defeating the whole purpose of this exercise. One of the shortcuts in SOLIDWORKS to repeat the last process is if you hit enter, it will reapply the same operation that you just did. So in this case, I do the thicken, and then to repeat the process, I just hit enter when I've selected a new surface to thicken. Once everything has been thickened, now you need to save the file before you can proceed. So I'm just going to make a new folder and put it on the desktop and call it something like robot. Now in the solid bodies folder in the Design Explorer, you can save all of the individual bodies that you've created into separate files. SOLIDWORKS automates this process so you can quickly generate new file names. But what it also does is it allows you to create an assembly. You may have even missed that option, but what it does is if you supply an assembly name, it will save all the files and then put each of those newly created parts into an assembly, fixed in space right next to each other. And so now you can take this assembly and you can now define the kinematics by creating mates between each surface that you want. And so you can deselect all but perhaps one of the bodies, and then you can kind of drag them a little bit out of the way so that you can see what you're doing, and then reassemble them. When you're creating a mate, you need to define several things. In this case, I choose the top surface as the mating entity because it's frankly quite easy to do so. In general, if you wanted to create a perfect kind of representation of a laminate device, you might pick the midpoint of, or the mid-plane between the top and bottom surface. And this would have the effect of being a little bit more kinematically realistic. Now, however, right now I'm simply just doing this for a quick demo, so I don't care as much. Also, because this is a one-layer device, it matters even less. But you need to do two constraints. One, which is an edge constraint, which defines the axis of rotation, and another, which is a point constraint between 2 points on neighboring bodies, which defines the translation along that rotational axis. Once you've defined those two things, you've pretty much defined how a hinge works in such laminate devices. So you can see I'm slowly adding the arms and legs. One of the things that I missed was actually creating a vertex to position the arms, so I give it a spacing from the top of the head. Normally this would have been supplied in the sketch itself that drove this whole drawing, but I forgot to do that. So instead I'm just giving it an offset from another point. And in this case I think it's 15 millimeters. So once your kinematics are defined, you can now move this device the way that it should move in reality once it's manufactured. So you can see that the arms move independently, as do the legs. And one of the things you'll also notice is that I didn't redefine every single joint, because I actually want some things to be separated from each other, like the second link of the arm as well as the legs. And so they're a little bit more free to move, and actually they wouldn't be able to move very well independently if if I had joined all of those edges. So now you can see the little robot in a neat position. Now if you're going to be exporting this into Pop-Up CAD, you actually need to reflatten everything so that when you export, you're able to export kind of the perfect face, the perfect geometry of each face as represented in the manufactured position. So what I do is I do coincident faces between neighboring bodies, and this will fully define the robot, even the hinges that I eventually want to move. So I've created my flattened device again. The next thing to do is to create a drawing which will be used to export the top surface of this device. You can simply drag in a top view, since I created my drawing in the top plane originally. Now I've created a little macro in SOLIDWORKS which can be used to export, and there are a couple things that you need to do to make sure that this macro works. First of all, you need to have created an assembly of parts that are solid bodies. The next thing is you need to have flattened them. And then the third thing is you need to create this view and select the view before running it. And so what happens is, if you've selected the top view, it will export a file consisting of all of the polygons that are in that view into a human-readable YAML file, which can be read by Pop-Up CAD. So in opening up Pop-Up CAD, you create a new sketch, and a sketch is just simply how you do any drawing in Pop-Up CAD. But in this case, since we've exported something that is readable by Pop-Up CAD, you can bring it in. There are a couple default dialogues that pop up at this point, which probably won't in the future. And you see that this is the robot. Now, because it's bringing in individual polygons, anything that is very close to each other, it's going to merge. So some things it thought were so close that it actually merged them. So we need to separate them. And we also need to define where the joints are. And so by copying that original sketch, you use this function called getJoints, and that will find all the common edges and allow you to use the lines that are generated to create joint descriptions or to separate faces that are touching and merged. So what I'm doing right now is I'm deleting all of the lines that were generated automatically that aren't going to be joints. And I will do that, use those in a separate file to define all of the lines which are going to separate bodies. And I call that my gaps sketch. So I take that same thing, get all those joints again, and then delete the joint lines, which I actually put in the other one. So now I'll have two sketches, one consisting of all the joints and the other one consisting of all the gaps. And I can use both of those in different ways for defining my final device. So for the gaps, I can buffer them, creating small areas which I can use to remove material between the body sketch and the gaps. And then the second one I can use to define where the joints are going to go, as well as make another gap to make room for the joints that I'm about to place. So in this case, I've pre-designed a hinge design that I really like. I call it the supported hinge, and it basically supports, allows you to create supports across two bodies that are connected to each other. And so what I'm doing right now is I am using that joint sketch to place those placed joints. I can also stretch and scale them. So a laminate operation can be then used to clean up and remove all that material that defines the gaps, either between the joints or just between bodies that aren't touching. And then another laminate operation can be used to merge the placed joints with the cleaned up body sketch. So the next thing I need to do is to clean up some small geometries here around two joints that touch each other. So I'm simply going to just draw in a circle and place it right at the meeting point where those two joints meet. There are a lot of ways to clean up hinges. This is pretty much just the simplest one. So I use the constraint tool box to both locate the center of the hole as well as to make the sizes of the holes, or of the circles, equal, or the radii, as well as then to define the radius of each circle. So now I've created a sketch which simply is two circles, and I can use another laminate operation to subtract the holes from the kind of ideal robot geometry. As a matter of fact, it doesn't look so good that I'm going to just make those diameters a little different, a little smaller. Now when you look at it, it doesn't look so bad. So I'm going to save the file. The final step is creating the manufacturing geometry, which is going to support the device from the surrounding scrap. And this is done by creating two operations. The first is the sheet operation, which will basically define the original sheets of material which will define the entire device at the very beginning of the process. Once you do that, you can then create the scrap by subtracting the device from that original sheet. And the scrap operation creates scrap and splits it into three categories: that which is removable up, down, and in both directions. The final step is creating the support design, which is going to bridge the gap between the device and that scrap and hold on to the device in a way that is both removable and cuttable. So the support will give you access to those regions that can bridge that gap. And here you see the support. So once you've created both the scrap and the support, you can merge them by using a laminate union and combine them with the device. And this produces a supported device from the outside. The support operation also produces cut files, which can be used to separate the device from that support once after it's been laminated. And this can be used to check whether or not the manufacturing is valid, the manufacturing design is valid, by removing a small outline cut from the supported device. The identify bodies function can then be used to check that you actually have separate removed bodies of material, some of which include the web and one of which includes the final device. And in this case, body 1 is that final device. And you can see it in a close-up view that it includes all of the features that we designed, and that concludes the demo.